All right, welcome back everybody. We are here again in Studio Winston for another CENG 113. Show me a quick yes, no in the participants window if you can hear me and see me. Cool, looks like pretty much everybody. So we'll get started with the actual content for the course today. So the daily schedule notes that we have 2 lectures on Wednesday. That's because the one that you're in right now is what's our usual 4th hour. And the 4th hour is not really any different from any of our usual lectures because all of the lectures are primarily intended to be example based, right? So there's not a lot of derivations and things that we tend to go over in the lectures, although there will be times where we will have to do that. So we're just going to use it as more example periods. And I've also learned that my pop filter has shipped. So we should have a pop filter here in a couple of days. As noted on the title card that we've got here, please keep in mind everything's recorded. So you can always show up a little bit afterwards and then go check the videos to see if you've missed anything. I'm posting both of those, or posting the videos both on Zoom's platform, which is actually kind of nice because it has a searchable transcript, which they auto produce. I'm not supplying that transcript, so if it says things wrong, I didn't control that. But I'm also posting them on YouTube because I believe they're only they will only stay on Zoom servers for about 30 days. And so I want you to keep access to them. So you can always check out the YouTube ones. The links to the Zoom videos will probably expire after about 30 days. And I'm not going to try to keep those around because we've got the ones on YouTube already. Also noted, it'll be helpful if you have Matlab open today. So we're going to spend the first about 45 minutes worth of class just going over the basics of what you need to know for Matlab to tackle some of the initial homework problems and to get you ready for the types of calculations you would need Matlab for our first reactor. And we won't, or actually our second reactor. Both the first and the second reactor, and the third and the fourth, they all have significant Matlab components to them, but what we're going to go over today are the general ideas of what you would need for the first and second reactors, which will cover about 5 weeks of the course. So it'll be helpful if you've got Matlab open because we're going to be spending a fair amount of time in Matlab today. The relevant homework problems for today's lectures on homework problem or homework set 1 or 1.1 through 1.4, you are more than welcome to work ahead. Everything that we're going to cover is in the book. And so if you can read through the book okay and figure out what you need to, you can definitely work ahead. But I would say if you're doing about maybe a problem or 2 per day, you're probably in pretty good shape. You'll notice the homework looks kind of long. It's got 11 problems on it, but it's also not due for another like 11 days or something like that. So you've got time to do about 1 problem per day, 2 problems per day, something like that. And then we will have a little break in between lectures. We'll have fika. If you've never had fika before, we will have fika. And I'll tell you a little bit about fika in between the 2. So I am, let's see, might be a question. Can we take this might be a question for later, but can we take screenshots of the figures for the homework problems? Yeah, definitely. You can work everything on a piece of paper if you want, and then take a picture of that and put it into the document. That's perfectly fine. As long as just make sure we can read it, right? If you're looking at the pictures, we should be able to read all of your text pretty easily. It also helps a lot if you box your answers. Makes it easier to find. So I'm going to switch screens over to our Matlab. Let's get started with that. Let me move this one and move this one. So the screen that I've got set up here for Matlab is, maybe it's a little bit different from the one that you might have by default because I've sort of scaled it to fit the screen a little bit more appropriately. The major elements of Matlab that we're going to need, we're going to be writing a lot of scripts. So the majority of the homework problems that you would write in Matlab are usually best done in scripts. If they're quick plots or something like that for your own benefit, maybe you'll use the command window down here. Maybe if you're trying out syntax for something, or you're analyzing a problem partway through, maybe you'll use the command window for that. But for the most part, my guess is we'll focus a lot on scripts. And then I'm also going to demonstrate a couple of the useful things with the workspace. And as we go later in the course, I'll introduce a few new functions that we'll need in basically the same way that the book does. Because it's my book, I wrote the book. As well as a couple other tools in addition to just functions that can help you write better functions and write better scripts and things like that. And then later today, we will actually have a chance to practice some of these in more of the type of environment where you're actually expected to solve problems. So in this particular case with equilibrium reactors. So we'll get a little further into that in the second part of today's lectures. So those are the major windows of Matlab. I'm going to give this sort of lecture assuming that you've used Matlab before, because it is a prerequisite. How do I get the figure window to show adjacent to the script editor? If you click on the top right of your figure window, there should be a minimize, maximize, undock, or dock. If you click dock on there, you should be able to dock that, and that'll pull it down inside of here. So a couple of things. First, the plot command is the same one that we've always been using. The general syntax of plot is you give it two sets of vectors, right? You're going to give it an x vector and a y vector. They can be row vectors or column vectors. It doesn't matter which way that you send them. And then it'll plot more or less anything that you want it to plot, as long as you supply data points in that sense. So if you just do something like 1 to 10 and 1 to 10, it'll just give us a straight line, which is not particularly exciting, but whatever, that's a straight line. A couple of things about your plots. The bare minimum of the information that needs to be in your plots, which we're going to skip obviously when we're demonstrating it because it takes a little bit of time. But the bare minimum of information that has to go into your plots when you're submitting them is an x-axis label and a y-axis label. And so you'll get those with x label, so you can call it, my x label. You give it a string, and you can do the same thing with a y label, my y label. Something like that. That's the bare minimum that should show up in your plot so that people know what's being plotted. Those labels typically are variables with their units, but sometimes you just have a short phrase or something like that that goes on top of there. Titles are optional. Legends, you don't need those unless you've got more than one data series on there, and then you should have a legend that's on there as well. If you want to add lines to it, if you overlay those, if you want to overlay those lines on top of the existing plot, then you call the hold on command, and that tells Matlab place the next plot command onto the same figure. And so if I wanted to plot, say, a horizontal red line from 0 to 10, maybe at 5, I could do something like this, and it would add my horizontal line on there as well. Only now would I need something like a legend, where I actually describe what's on there. This was the first set, or first series and second series. All of this is covered inside of the book in chapter 1, so that all the common plot commands are in there. Very often, a command axis square is helpful. It takes the two aspect ratios of it takes the aspect ratio of your two axes and makes them equal to each other. Most likely, we will use axis square on all of our plots. Usually, again, we're not going to use a lot of the command window because we're going to build up some fairly lengthy analyses, and we don't want to have to write those in every single time. And so we can take any of our commands here and put them up inside of a script and save that script as something. And now it's just Matlab's way of saying you can run that script, and every time you run that script, you're running exactly those same commands each time. How does Matlab know which legend title belongs to which data set? It goes in the order that you added the data sets to the plot. So we did the blue one first and the red one second. So the first legend entry here was for the blue, and the second legend entry was for the red. It just follows whatever the plotting sequence happened to be. There are ways to mess around with whether or not they all get shown or not, but I usually just have to Google the documentation in order to remember how to do something like that. So if we, how do I add the figure tab to my Matlab window? Your figure tab might not be in your Matlab window. It might have popped out. If you want to add it to your figure window, click on the little triangle in the top right of the figure window, and you'll have an option that says dock. And if you dock it, it will put it right next to everything else. You might have to kind of readjust a little bit in order to get it to show up. I honestly don't use Matlab looking like this very often because this is squished a lot just so that everybody can see everything. And it doesn't need to be docked. Everything will work just fine if it's not docked. You also won't see it if you haven't plotted anything, and it doesn't just show up unless you've plotted something. So with this script, the way to interpret this is MATLAB is going to run through this from line 1. It'll run line 1. It'll then run line 2. It'll then run line 3. It'll then run line 4. It always goes from top to bottom of the script, with a few exceptions that we're going to investigate in a minute. And so obviously the advantage of this is I don't have to keep re-entering this data over and over and over and over again. I can just write it once in a script and then make small changes to the script as I go. So as an example, let's see how to plot heat capacity. So you probably remember that a lot of heat capacities are given in polynomial forms that look like something like this: A plus B times T plus C times T squared plus D times T cubed. And suppose we would like to plot that. If we wanted to do something like that, I'm just going to delete the rest of this. We would have to look up what those values are of A, B, C, and D in order to actually plot this thing, obviously. So we're going to have to look up some amount of data, but we're not going to do it from our book. So one of the things that's interesting about the book that we're using, and it's not just the book like this particular book does that, the majority of reaction engineering textbooks assume that heat capacity is not a function of temperature. I'm bending that rule a little bit here just so we've got something to plot. But as we'll see later, actually today, we will, going forward, always assume that heat capacity is constant. So if I were to look this up for methane, I would find that my coefficients are these values: 213 e to the minus 2, 1.197 e to the minus 5, and minus 1.132 e to the minus 8. Where did those come from? I just looked them up in a book somewhere. Pick any thermo book that you've got. It'll probably be in the back of your thermo book. And under these conditions, the heat capacity that we've got here, C sub P will be in units of joules per mole Kelvin, and T is in units of Kelvin. What I've got up here at the top in green is called a comment block. It's a useful way to kind of summarize the parameters of your problem before you get started. MATLAB will not execute anything that's green. Anything that is a comment is skipped by MATLAB. So if we wanted to just calculate a value, we can copy these. These are the values that MATLAB will actually use. Semicolons at the end of your script they're not just for looks. They can actually help you track down errors because otherwise things print out like mad. Suppose we want to calculate this at 300 Kelvin. How's that background noise? There's somebody else talking on the first floor. Is it, if you clear your yes, no real quick. Actually, ooh, here's a good one. Over on your participants window, if you look under more, there should be an up thumb or a down thumb. Can you hear the people talking in the background right now? I guess thumbs up if you cannot hear them, if everything is okay. Thumbs down if you can hear them and it's distracting. Oh, it's a little bit of both. It's half and half. It's fair. I'm going to angle my mic a little bit away from them. Okay, so if we wanted to calculate heat capacity at 300 Kelvin, actually, hold on just a second. I'm going to step aside here for a minute and see if we can fix this. Let's rock and roll. So let's say that we wanted to calculate heat capacity at 300 Kelvin. We would copy our form of the heat capacity and put it down here. And that could be our script. And so what MATLAB is going to interpret this as is create a variable called t, give it the value 300K, create A, B, C, and D, assign them to the values that are here, and then calculate the heat capacity. It's very helpful to get into the habit of adding units afterwards, because as we go, the units will get more and more complicated, and it's nice to have a little annotation on there so that you can quickly check the units of things. If I save this as a script, and then run it, so you're not going to be able to see me running them, because I usually run these things from my keyboard, but all I'm doing is up here on your editor ribbon, I'm essentially hitting the run button. But if you hover on the run button, I'm not sure if you can see the pop-up script through Zoom or not, but if you hit or hover on your run button, you'll see that there's a shortcut for it, which is F5. At least that's what it is on the Windows machines. It's probably something similar on Mac. And so I usually don't come up to editor and actually hit run. I'm usually pressing F5 on my keyboard because that's a little bit faster. And so what we're going to see is that these variables are going to pop up over here in our workspace, and it's going to calculate a heat capacity for us. So I'm going to hit F5 on there. Oh, I forgot to put multiplying signs in here. There's the usefulness of an error message. It'll actually tell you what went wrong. And so now we can see our heat capacity is calculated down here as about 35.66. I can always check it. If I type C sub P from my command window, it'll just print out what C sub P is. If I hadn't put the semicolons in there, it could have been harder for me to track down this particular error because they can get pushed off of the screen very quickly if there's more errors or more warnings or things are printing or something like that. One trick that I happen to do fairly regularly, it doesn't matter very much when you've only got what we call scalars, which are just a single number, but it helps a lot more when you have like vectors and matrices. If you double click on any of the variables in your workspace window, let me dock this thing just so we can see it, dock variables, put it over here. If you double click on it, then you will be able to investigate the actual value of the heat capacity. And so you can actually enter numbers in over here. I don't know why you would do this, but you can just enter the number 16 and it'll suddenly turn this into a giant matrix. So it can be useful sometimes to look directly at the values. If I were to run this script again, and now look back over at my C sub P, I can see that it's changed back to 35.6607. There was a couple of questions in the chat. I thought it was t to the -2 when d is the coefficient. It could be. It depends on what book you went to. These polynomial forms are different in different books. Some of them have a natural log term sitting out here on the end. Some of them have a negative exponent up in the top. It just depends on where you got it from. My book, the one that I was looking at, had this particular form. Actually, there's yet another form. You'll see it. If you look back in your appendix, there's a really cool appendix. So these heat capacities for ideal gases are all calculated theoretically. They're never actually measured. And the form that they use comes from a combination of statistical mechanics and quantum mechanics. And you can see that the form that tends to be used for quantum mechanics is way back in Appendix C2. If you read through there, you'll see that there's like a bunch of hyperbolic sines and cosines. That's the actual form that is sort of the most natural for the data series, but almost everybody just uses polynomials because they're easier. Anyway, that's all on a side. We're just talking about stuff there. Another question, do you need an asterisk in the CP equation to make it so they are multiplied? Yes, I fixed that with my B. If we wanted to calculate heat capacities over a larger variety of temperatures, so perhaps we want to plot them, we can turn our temperature, instead of a single value, we can make it a vector. And so I'll just say Linspace from 250 to 350. Linspace will give me an even distribution from one to the other. This, though, is an example of vectorized, well, it's one step in creating what we call vectorized code. If you ever want to use vectorized code, then you have to use what's called element-wise multiplication. And generally, we use element-wise multiplication all the time. The only time we don't use element-wise multiplication is when we're being very careful to use matrix algebra, and that's not going to come up terribly often. There is an appendix in your book. Matlab has some pretty useful capabilities when it comes to matrix algebra. So if you look at Appendix B in your book, you can see some of the ways to speed up our code by using vector formulations in Matlab. We're not going to be anywhere near that for about 2 weeks, though. So you can read it if you want to, but we're not going to use it. Element-wise multiplication is to add dots before any multiplication or any caret operators, raising things to powers. And that just tells MATLAB, do this operation once for each one of the elements inside the vector or matrix or something like that, as opposed to not having the dot. If you delete the dot, then you're actually asking MATLAB, do the thing that's called matrix squaring or matrix cubing or matrix multiplication. And we usually don't want that. And so we put dots in front of the multiplication symbols. So if we have something like this and I run the script again, and I look at C sub p, I'll now see that it's a vector. And in fact, it's the same shape as the vector in t, right? If I look at t in my variable window, it goes from 250 on up to whatever, and each of the corresponding heat capacities for those temperatures are in the same relative location inside the heat capacity vector, which is what I want, right? That's the only way that I can plot something, is if they have the same number of elements in their vectors. I can also double check down here in the workspace window down here and see that the heat capacity vector has 1 row and 100 columns. That's what 1x 100 means. And the temperature vector is 1x 100 in size, which is 1 row and 100 columns, which is what we want. If you want to add increments to, how do we add increments to Linspace? The third argument sets the number of number of inputs. So, or sorry, number of elements. So if I only want 5 elements, then I would just do the number 5. And now if I look at heat capacity, I've only calculated it at those 5 values. Usually that's not enough when you're plotting something, which is why I tend to use the default for Linspace, which is 100. So if you were to type 100 here, or if you just leave that argument off, right? If you just leave it like this, that's the same as asking Linspace to please provide 100 elements. If you wanted to provide 250 is a little bit weird because that's one of the other numbers. Let's just say 100, just to keep it on there. You can adjust that to almost anything you want. The colon operator is not a bad one, but we tend to use Linspace more because we tend to know what the endpoint is and what the starting point is, and that's a useful syntax for Linspace. If we then want to plot these, we give them in the order of what do we want to plot on the X, what do we want to plot on the Y, and that will plot everything we want. I'm going to close this figure real quick, run this, and dock the resulting window. So there's our plot. And of course, we would add annotations like this. And that's sort of the minimum that we have to do to make sure that the reader, or anybody, in our case, the grader, but anybody who looks at your plot actually knows what's being plotted here, is to add axes labels with an X label and a Y label. All kinds of other annotations are given in the book in chapter 1. So if you go to around page 19, 20, something like that, there's a table in there of lots of different plot annotations. But this is an example of a script, right? And most of the things that we're going to analyze in here are most conveniently represented as a script. Often it's going to be easier to create what we call local functions. It's kind of rare. In fact, I don't think any of the examples that I'm going to use anywhere in the class have their own dedicated function. I use local functions everywhere because local functions are a good way to organize your problems, right? I can have this one script do everything I need for a single problem. Any functions I want to write or anything like that, I can tuck them all into this single script, and then I don't have to worry about multiple scripts and multiple functions flying around or something like that. I also don't have to worry about renaming functions, which is surprisingly annoying. Coming up with unique names for functions is hard when you're developing like 7 or 8 functions all at once. The syntax for a local function is a little strange if you've never used it before, but it's easy to remember. It's easy to remember because local functions always go at the bottom of a script. So when I write a script like this top portion that we have up here is what we would call the script portion of the script, right? That sounds a little bit sort of circular, right? It's the script portion of the script, but that's to distinguish it from any of the local functions of the script. You do not need these double parentheses to get that bold notation on there. That's just my way of dividing it. It'll work just fine if you don't have those double parentheses on there. And so a local function is just a way to write a function that's only accessible to the stuff that's inside the script. So for example, we would probably want to write a function for heat capacity so that we don't have to keep copy pasting this, right? What if we want to write calculate a heat capacity at another temperature and then another temperature and another temperature and another temperature? It gets a little bit tedious to keep copy pasting this over and over and over again, although that's certainly doable. An easier way is to write a local function so that we can just pass a temperature to the function and out pops a heat capacity. There's a question in chat. Can you have multiple local functions in one script? Yep, you can have as many as you want. I mean, within reason, right? If you have 500, it might be a little bit hard for you to track them down, but there's no fundamental limitation that I'm aware of for the number of things that you can write as local functions. The general syntax for a local function looks very similar to the syntax for a function that you've probably written before, which is just this, right? You say function is equal, or function followed by whatever you want the output to be, give it a function name, and then whatever you want the input to be. So if I want to write a function to calculate the heat capacity, I might name my function CP, and the input to that would be T, and the output I'm just going to leave as output. It's depending on the complexity of your functions, it's useful also to indicate what the input is supposed to be and what the output is going to be. But yeah, you know, it's your call whether or not you want to do that annotation. I'm in the habit of doing it because it helps me catch mistakes, but it's not 100% required. So I can take this same piece of code here, put it down here, and say that the output to this function is going to be a plus b times t plus c times t squared, et cetera, et cetera. That's perfectly fine. It's up to you if you want to label your functions like this. I'm in the habit of actually not doing that, but whatever, it's okay the way that it is right now. And so now if I want to plot the heat capacity or calculate the heat capacity, I can come up here. This is actually the reason why I can't do this. Let's change this around. I don't like calling it the name of the thing that it's calculating every time because sometimes it gets a little bit tricky to calculate things or to understand what is a function and what is a variable. So I'm going to call the function myfunc just so that I don't have to worry about having multiple c sub p's floating around. So now up here, I can say myfunc of t. This is why I changed the name of the function. If the name of the function had been c sub p, this would have looked like a really unusual line, right? It would have said c sub p is equal to c sub p of t. That's a weird way to write something like that. If you can make it work, go for it. But generally, you should never have a variable that's the same name as a function because it can get confusing for Matlab to figure out what's going on. And so I can call it myfunc of t. I don't need any of this anymore because all of that is being handled. Oh, wait, I have to put those inside of my function like that. And now I can calculate heat capacities for any number of temperatures by using my local function, which is a little bit more convenient. So if I run this, the plot actually won't change at all because it's doing exactly the same thing that it was doing a moment ago, which is exactly what we wanted it to do, right? We didn't want it to be any different. This structure that we've got here, where we've got a script portion up at the top, and we've got any number of local functions down here at the bottom, that's a really nice way for you to organize your work. And so if you look inside the book, this is what's being described in section 1.3. And that's what you're going to see in almost all of the examples that I do, and all of the examples in the book. They're going to have a structure that looks like this, with local functions on the bottom and script portions up at the top. And that's going to come up pretty frequently, because it's a very useful way to organize things. As an example of how we might use a local function, one thing that you're going to have to do pretty frequently is to solve an equation for an unknown. And this is a procedure called root finding. And I'm just going to give you a quick overview of root finding. Sorry, there's one other question. Doesn't the local function need to be defined before the script portion, or does it do that automatically? That's a really good point, and it's the weird thing that's easy to remember, but also easy to forget. If you're using local functions, they always come at the bottom of the script. And that's just a syntax definition that Matlab has. Most languages actually use their local functions in a similar manner. So for example, Python usually puts all of their local functions down at the bottom of the script. So no, it in fact cannot be defined before the script portion. You'll get an error if you try to run it that way in most cases, because it can't be defined that way. So the local function actually comes afterwards. I thought you had to name the script after the function you're using. You have to name a function after the function you're using. The script can be called anything you want. So my script is called my script. The local functions can have any name that I want them to have. That's one of the advantages of the local function syntax, is they can sit inside of a script and you can call them anything that you want, which is convenient because I often recycle names over and over and over again. Let's say, for example, that we wanted to figure out what's the temperature at which the heat capacity here is equal to 36 degrees. So for example, or sorry, 36 joules per mole. For example, if I wanted to add this on here, let's say 250, 250, 350, and then 36, 36, blue. Perhaps we want to know what's the value of temperature, which produces heat capacity of 36 joules per mole per Kelvin, which is the equivalent of the intersection of that red and blue line. That's a procedure that has the formal name called root finding, but really all that is guess and check. And so the way that root finding works, I'm going to flip over to my handwriting screen here for a minute. You don't need to really know too much about root finding in the sense that we have a function that's going to do all of the root finding for you. But it's useful to know a little bit about root finding when it comes to understanding why certain things are being put into the script in the way that they are, or into the function the way that they are. So root finding, let's make this black, is a fancy word for solving an equation. We say the word root finding because that's what the mathematicians came up with, but we're trying to solve an equation basically for x. And so if we have, if we take our example, we're not going to be solving for x, right? We're going to be solving for t, because that's going to be the thing that we want. We have a function for heat capacity, which is a function of temperature, and we want to know what's the value of temperature when that function is equal to 36, right? So our question is, how do we figure that out? One way to do it is just by guess and check, and guess and check is a perfectly appropriate way to go about it. You just start picking values of t, you calculate the heat capacity, and then figure out whether or not it was equal to 36. If that wasn't right, then you go back and you calculate it again. The way that most root finding algorithms work, though, is to try to find what's called a root, which is a 0. And so they will take this expression and rewrite it in what's called root finding form. And this is what you'll have to do anytime you want to ask Matlab to solve a problem for you. And so those all generally look like a form of f of x is equal to 0. And so it's really easy to make things in root finding form. For example, for the problem that we've got, we can just pull the 36 over to this side, and the result will be equal to 0. So we could say this is equal to C sub p of t minus 36. Right, and so the equivalent of guessing temperatures and finding out when the heat capacity is equal to 36 is maybe instead I guess temperatures until I find out that this quantity, Cp minus 36, happens to be equal to 0, and that's how root finding functions work. Root finding functions, the most common ones that you'll use in this class, actually you'll only use one in this class that I will teach anyway, are fsolve. Another one that you may have used in the past was f0. F0 is like a kind of a subset of fsolve. Fsolve can do everything that F0 can do, but F0 can't quite do everything that fsolve can do. Namely, fsolve can solve for multiple unknowns, and that's what we're after. And so the syntax for fsolve will be give it a function and give it an initial guess. Right, and the output of fsolve is going to be the value of x, right? It's going to solve that that function or that equation. This is what we would call the root. The guess that's over here, that's just because you got to get started somewhere, and so you need some intuition about where that root ought to be, where the solution ought to be. Usually, the easiest way to get this is to plot f of x. And then you look for the zeros, right? And you can just do this right in Matlab as we did a moment ago. We're just looking for the zeros. You only got to get like kind of close, right? You don't have to get particularly close if you're typically within, like plus or minus a factor of 100 or something like that. That's probably close enough. So we can just kind of look at our x-axis and the previous plot and figure out a good guess for x. The function that you're going to do here inside Matlab, this is going to be a function handle. And a function handle is simply the word or the letter at followed by the function name. So whatever you name your function, give it an at that sits in front of it, and that is what goes into this first argument here, which is here, right? That's a function handle, not just a function. There are other syntaxes that you can use for it, but this particular syntax happens to be good for many problems that we're going to do for different reactors, which is why I'm teaching you this particular syntax. So these three processes here of you start off with an equation, usually a material balance, an energy balance, or some kind of inequality that you have to use. If you're trying to use fsolve and it says you need an optimization toolbox, then I think you'll have to download the optimization toolbox. I thought that was a core though. If you need a quick workaround, open the online Matlab and it'll have the one that you want. Otherwise, the warning or the error that just popped up when it said you need a toolbox should have a link in it, and you can click on it and download the link. But you won't be able to follow the next few steps. So you start off with the general equation you're trying to solve, right? I need to know the value of T for which the heat capacity is 36. You change it over into root finding form, which is very easy. You just move all of the things on one side over to the other side so that you get this form of 0. And then this becomes your function, right? This is now my f of x, and that's the thing that I'm going to plug into the fsolve function in order to actually find out what the value of x is, or in this case, t. And then the figuring out what the initial guess is for x. Sometimes you'll have engineering judgment for that. Like you'll just know that it's got to be between like 0 and 1. So you'll pick like 0.5 or something like that. But more, I guess, consistently, you can get a good estimate by just plotting it. And so that's what we've already got on the previous screen. So if I'm going to take this fsolve syntax and I'm going to put it right into Matlab. So I'm going to switch over to Matlab right here. If I wanted to add this to my script up here, T solution, I'm going to name it something different because I don't like to recycle names. T solution is equal to fsolve. So if I leave that parenthesis open, it's asking me for the next few inputs to fsolve. I don't know if you can see the pop-up through Zoom or not, but it's showing me what the syntax is because I've left that parenthesis open. It's asking me for the link to my, or the anonymous, or the function handle to the function I want, which I called my function, my func, and it's asking for an initial guess. If I look at the plot that's on the right here, it looks like that value ought to be somewhere around 300. So I'm just going to guess 300, right? It's probably somewhere close to 300, but I'm going to let the fsolve function actually find out what is the value that I'm interested in. And then I also need to modify my function to make sure that it's in root finding form. Right now, the function is outputting the heat capacity directly. I don't want it to output the heat capacity directly. I need it to output the heat capacity minus whatever the target is. So I actually want output is equal to output minus 36, right? I don't want the value of the heat capacity where it is 0. The heat capacity itself will not be equal to 0. I want the value of the temperature at which the heat capacity is equal to 36. And so this is root finding form. You can equally say, you know, if you don't like that command, if this looks weird to you, to say, what do you mean by output is equal to output minus 36? That's okay. You can ignore that and then just subtract off 36 from the line above it, and that's entirely equivalent. I'm getting a hint that you're going to need the optimization toolbox. The two people have asked whether or not you need the optimization toolbox. You may, in which case you'll have to download it. Or you can use the online version, but at any rate, you should have free access to the additional ones. Can you put minus 36 in the fsolve argument? Yes, you can do it there as well. Any of those would be equivalent. This is actually a good option to say, how many weird things can I do? Try all kinds of different variations to get this thing in root finding form. And if you get the right answer, it was probably okay, the way that you did it. So for example, if I were personally doing this, and this is for my own benefit, I would write this way, right? Because for me, this separates all the different ideas. It says, can I quickly check whether or not I've got the heat capacity correct? Yes. And then as a separate step, have I defined it in root finding form? Yes, I've got CP minus 36. But there's lots of different ways that you can write a function that way. So if I run this script, I should get a message. My plots have come up a couple. I'm going to disable my plots because they're not plotting what I want them to plot anymore. I should get a message that says equation solved. That's what I want to see. If I see that fsolve has reported that the equation has been solved, that means it's probably got a pretty good estimate of what that value is. And if I look at t solution in the variable window, I'll see the t solution is 306.0312. There's actually a ton of different or a ton of extended precision on there, but MATLAB just rounds it to 4 decimals all on its own. And so that's an example of root finding. We have now found that the temperature at which the heat capacity, in our case for methane, is exactly equal to 36 joules per mole per Kelvin, is about 306 degrees Kelvin. And I say about because it's a numerical approximation, right? It's getting pretty darn close to that value, but it's not dead on. There's a little bit of noise in there, but it's usually accurate to like 1 part in a billion or something like that, which is close enough for everything that we would be worried about. So if I'm interested in only solving this for a particular value, then my script would look something like this. And I really only need one step, right? It's just fsolve. I need a lot of other steps inside the function, but that's the way that it goes. That's the syntax for using fsolve. There's a lot more that fsolve can do, most of which we won't need until we get to solving for multiple unknowns. One of the homework problems later on will require you to solve for more than one unknown. And so that's a syntax that you're going to have to look to section 1.6 in the book to review. It looks very similar to this, except the inputs become vectors instead of scalars. And I've got some worked examples in the book of how to solve for multiple unknowns. So if there was one temperature at which 4 or 5 different heat capacities were all equal to 0, there is a way for me to solve for something like that, if that happens to be the case. Or excuse me, if there's say, a temperature and a mole fraction, and I need to solve a material balance and an energy balance simultaneously, FSolve will do that for us. And that's also why I choose to teach you FSolve instead of F0, because F0 can't do that, which means that it's not good enough for what we need it to do. This form, however, that'll be plenty for anything that you're going to do on the homework problems that I've noted for this particular set of lectures, which is 1.1 to 1.4. This syntax will be enough. So you can focus on this kind of a syntax, and then when you get to the later problems and realize I have 2 unknowns and 2 equations, you can come back to this and read through the book and find out what the fairly minimal modification is that I need in order to get multiple equations solved all at once. So we are just about at, actually, I think I said the original FICA would be at 2:45 and it's 2:47. So let's go ahead and switch over. I'm just going to take a break here. Lecturing for 2 hours is a long time. I think everybody needs a break. I'm just going to switch over to a different screen here. Nope, don't want to share that. I'm going to share a portion of a screen, share a little bit of sound. This is fika. So fika is a Swedish word. It's like more of like a verb than a noun. Fika is something like a coffee break where you just sit and socialize for a little bit. You don't work during fika. That's the point of fika, is to relax for a little bit. And we've got a little bit of time in between this lecture and the next one. The next one starts at 3 o'clock. And to just kind of keep plowing through everything for 2 hours is a little bit much. So I'm instituting fika on Wednesdays. So Mir and Winston Churchill are joining us, as you can see on the screen there. Mir is the guy in the pillow, and Winston Churchill is the little guy on the back of the couch. And they're going to join us for fika. Little Winston might be around us. I think he's behind us. But I'm actually going to make a little bit of coffee for fika, because that's what you do in fika. So feel free to get up, stretch your legs, ask me questions in chat. I'll try to answer them as best I can. But I'm just going to sit here until about 3 o'clock, make myself some coffee. Notice that fika also involves something sweet. So for today, I have myself here a little chocolate chip muffin, because that's pretty sweet. So I'm going to brew myself a little bit of coffee, relax, do whatever you want. We'll start up again at about 3 o'clock. I'll turn on some little bit of background music. Again, feel free, shoot me a question in text if you want. Get up, walk around, have a snack. So this is Winston. He's very tiny. There he is. Say hi, Winston. Yeah, he's also very sleepy. He was sleeping behind me, and he was not pleased to be woken up. But this is Winston. We are here in Studio Winston, and Winston and Mir will be joining us for fika on Wednesdays, but only on Wednesdays. Winston is 2 years old. He was a rescue from OC. I don't know if you heard about a hoarding situation up in OC. They found like 150 dogs or something in a single house. And so they sent out a message. Oh, thank you, Winston. Thank you. They sent out, oh, that means he wants to get down. The rescue organizations up there sent out a message saying, you know, if you can adopt somebody, please do, because they were overwhelmed with this hoarding situation. He wasn't one of the 150s. He was already in the shelter at the time. How old's Winston? Winston is 2. Mir, the old man, is 13. So Mir usually doesn't like to come onto the stream. He's downstairs right now. Oh, Hannah, the question that you've got, you may be missing the end statement at the very bottom of your local function. It needs an end at the very bottom. And then make sure everything beginning from the word function all the way down to that word end is all put down at the bottom of the local script, or of the script. That's not a problem of missing the toolbox because it actually gave you the error. Otherwise it would have just said, I can't find that function. Dora, what you're asking for is fine. Was the name of this music? The name of this music is, it's called Sneaky Snitch. I'll put it in post. Oh, there's my coffee. If you ever find yourself with an extra 10, 20 bucks, go on Amazon or something and find yourself an electric kettle. If you drink tea or coffee, get a little electric kettle because it's really convenient for making just the right amount of stuff for 1 or 2 people without having to brew like a whole thing of coffee. So I have a little coffee cup. This is my favorite, one of my favorite cups, by the way. It's for a hospice organization, which is a little bit morbid, but I like it. Do I ever play online video games? Yes and no. I don't stream, but I watch streamers. And so I actually went through a fair number of their websites and looked at the equipment that they have. And I forced the department, well, I didn't force the department. I asked the department, I would like some funds so that I can get an appropriate system for remote lectures. And I just didn't tell them where that information was coming from. But streaming is sort of a solved problem, right? Streamers know how to stream. And so I looked at their equipment and used that. I'm using Matlab Schemer to add a color scheme to my code when I'm copying it. Some of it's illegible. If it's, I would say maybe don't use that color scheme if it looks illegible when you copy paste it. You can try a screenshot though, right? If it looks okay on your screen, you can embed the screenshot, but just keep in mind if you do that, it can be hard for us to see what you're doing. Oh boy, I hope I didn't make too much coffee. I forgot. Okay, should be fine. I should start streaming now. I play a game called Diablo 2. Actually, a variant of Diablo 2 that's online and it gets streamed sometimes. But the the guy that I watch most often is already a pretty fantastic Diablo 2 streamer. I would feel bad trying to compete with him. Plus, I would probably not do particularly well. Is there a way to save Matlab online scripts as a plain text to upload to Microsoft Word? I know you can always download it as its Matlab file, the .m, and then just open it in a text editor because it's just a text file with a different extension. Yep, there you go. Yeah, so rename it to a .txt file. And then you can copy paste that directly into it. Am I excited for Diablo 4? I am cautiously optimistic for Diablo 4. I wasn't a big fan of Diablo 3, but you know, fingers crossed that Diablo 4 will be pretty good. The name of the music that I had playing at the beginning of the first lecture, it was probably one of Kevin MacLeod's, if that's how I pronounce his name, one of his songs, because his are all royalty-free, so I don't have to worry about, or I shouldn't have to worry about anybody on YouTube making a copyright claim to it. If you scroll up in chat to the one that I sent to the whole class, his name is in there. I don't remember exactly which one it was. He's only got about a dozen or so. Or actually, that's not true. He's probably got 50 or so. I'm sure you'll find it. Some people have looped Kevin's music for, like the one you're listening to now is, this song itself only goes for about 3 minutes, but somebody loops it. In fact, I think Kevin loops it to an hour, and then some of them loop for 10 hours. And so if you're doing something, you just need quiet, repetitive background music, it's nice. What microphone do I use? I use I know it's a Blue, but I don't know what model it is, but the manufacturer is Blue. Play another song of MacLeod's. I will try to play different ones each day. Thanks, Santino. Anybody been in any of the other classes where all the nonsense is going on in chat? I've kept ours locked down a little bit because I heard people are not doing good things in chat. By the way, I can't see what anybody else is. I think I've turned off everyone's cameras, but I just keep the camera on a single person, which is myself, which is not an arrogance thing. It's just, it keeps me focused. So if you're worried about anything in there, just turn the camera on me. It was pole dancing in physics class. That's kind of messed up. I'm glad 101C went well. I think we can go ahead and turn off the just chat me thing. I'll enable it so that everyone can talk to anybody. Oh, I'm glad you're enjoying them, Andy. Yeah, Diablo's online. A lot of CENG classes are okay. That's good. How did I reformat my Matlab windows? I click and drag on the titles, or on the title bar of each of the windows I want, and you can kind of drag them around and move. Do I do any research? Or no, I'm what they call an LPSOE, which is a teaching professor. Oh no, I'm sorry to hear that, Heza. 40B wasn't good. Oh, geez, there's profanity too. That's never any good. Personally, I like it because for me, it's I don't have to shush anybody. Like we can just start talking, and you can text me directly, and so it doesn't, distract anyone else while they're talking. We'll get started about like 3:05 or something. I haven't finished any of my coffee. Yep, chat's open. We'll try it. If it gets weird, I'll just turn it off again. Like I said, I've been on Twitch a fair amount. Like I see how clever people can be with their ASCII art, and so if that kind of stuff starts happening, we'll just turn it off. I don't have any moderators on the channel. Oh, I'm sorry to hear that, Omar. That doesn't sound like a good time. My favorite Twitch emote, probably the ones that are specific to the channel. I usually am in Mr. Llama's channel, and he's got his own little cute blue llama emotes. My favorite color? Blue. Although black's nice too. Black matches everything. It's great. No, I've not thought of focusing in pharmaceuticals, but I'm always impressed by the people who can do the bio stuff. You might just be here for the second lecture, Yashing. We have the Wednesday 4th hour is 2 to 3 or 2 to 2:50, which is right before this one. Don't worry, it's all recorded, so you'll be able to check it. All right, I noticed a potential problem. I think I'm going to lock up chat again, not because you're doing anything that's wrong, it's fine. But I can't tell who's messaging me or not. I know there's that little red privately message that's on there, but it's still hard for me to notice who's doing what. So I'm just gonna button it up while I'm talking. so that if you want to send me a question through chat, then I'll be able to quickly see that you sent something, and then I can actually answer it. So I'm just going to switch that back over to just me. All right, let's get started with the next topic. Let me switch over to, this time, the book. So the first reactor that we're going to look at is actually a reactor that we've seen before. You would have seen it in your thermo class at some point. Whether or not we actually called it this kind of a reactor, maybe that's a different thing, but it's just an equilibrium reactor. And so the equilibrium reactor is in chapter 2 of the book. Let me zoom this out a little bit. And that's where we're going to spend most of our time, at least today, and all the way up until, if you look at the daily schedule, until we hit our next reactor, our next topic, which is rate laws. We're going to be hanging out in chapter 2 for a little while today. Most of this should be review of one form or another. It's mostly listed here in the book, so that if you have a question about the way that one of these things were derived, you can always go back through the book. It's all there in enough of a way that I think you can follow it, derived or defined. But what we're mostly interested in is just a review of how do you use this stuff. And when we say an equilibrium reactor, what we mean by an equilibrium reactor is some amount of stuff comes in, and then when it comes out the other side, it's at chemical equilibrium. All of our equilibrium reactors are going to be isothermal, although the requirements for equilibrium don't require an isothermal reactor, but all of our reactors will be isothermal, at least for equilibrium, which means that the temperature going in is going to be the same as the temperature going out. That doesn't mean we can't set the temperature to be anything that we want. It just means that once we set it, that's the only temperature that we're going to have. The key equation that we have that underlies all of these discussions of equilibrium is this one here, equation 2.7. I'm going to zoom in on that because it's important, which is that the Gibbs energy of formation, the change in Gibbs energy of formation, if a change is possible, that change will result in a change in Gibbs free energy going down. If you can't make Gibbs free energy any lower, then you have reached equilibrium. That's our definition of equilibrium. One type of reactor that we're not going to talk about that sometimes we do if the campus asks us to move a little bit slower in the first week, and then I know it's crazy around here, so we would have done that anyway. One of the reactors we would have looked at is called a Gibbs reactor, which is section 2.3. And so you can just calculate G directly and plot it, right? And you'll just get a curve through it. If you're interested in learning about that, I've described that process here. And if you scroll down to example, what is this? 2.1. 2.1 shows you what I mean. You can just plot G, find the minimum, and that's equilibrium. And that's conceptually what we're doing in all of the other examples that we're going to work with, except we're taking a shortcut. If you remember from probably Calc 1, something like that, the derivative of this function G is equal to 0 down here at the minimum. And so the more direct approach, rather than calculate a bunch of G's, create a plot, and then try to identify the minimum, the more direct approach is take the partial derivative of G and find out when it's equal to 0. That should sound familiar, right? That is a root finding operation. It's saying find out when something is equal to 0, usually by changing some parameter that's related to the amount of stuff in the reactor. So maybe an extent of reaction, maybe a conversion. It could be lots of various things. The form that we use, and the form that's most commonly used because it happens to be really useful, is to take the derivative of G with respect to the extent of reaction, excuse me, which is what section 2.4 goes over. Again, this is more or less review. It's exactly the same principle actually that was used for phase equilibrium. It works for both phase equilibrium and for chemical equilibrium. So we're not going to spend a lot of time deriving all of this, but it has some useful equations that you should probably review for yourself. For example, the extent of reaction, which I believe the formal way to pronounce that is Xi, because it's a Greek letter. It sounds like KSI, but like a hard K. Some people pronounce it as Xi. You will hear me pronounce it as squiggle, because that's the way that I'm accustomed to working with squiggle. It's the same squiggle you would have used in thermo. It's the same squiggle you would have used in material and energy balances, it hasn't changed at all. And so what you get to eventually, as you go through all of these, is an equation that should look somewhat familiar, and this is where we're going to spend all of our time. You have a product of a bunch of activities is equal to a change in Gibbs energy. And at the point where this equality is satisfied, so this is equation 2.21, that means that the stuff inside of your control volume is now at equilibrium. Or you can say, what are the conditions at which equilibrium would be achieved? This equation, 2.22, 2.21, that's the one that defines what it means to be at equilibrium in an equilibrium reactor. And so what we're going to end up doing for the next few days is solving this equation over and over and over again in order to find out what the composition looks like at equilibrium. The reason we spend so much time with equilibrium is because it's sort of setting an upper bound on what's possible in your reactor. No amount of catalyst, no amount of messing around with pressures and flow rates inside of a reactor can ever beat equilibrium. Equilibrium is always there, and you can never do better than equilibrium. You can get different predictions from equilibrium. So, for example, some rate laws that we may find don't agree with equilibrium because they're only valid over a short range where equilibrium is not important. That could be the case. But for nearly every problem that we're ever going to do, this equation 2.21 is in its way defining the upper bound in terms of conversion that we can ever hope to achieve. It's split into two portions. And so today and potentially tomorrow, we're going to work just on the right-hand side, which is the exponential part. And then in the remaining 2 or 3 lectures, we'll work on the left-hand side, which is the activities. And so we're just going to be calculating the right-hand side of 2.21, the exponential of minus delta G over RT. We take this one, there's lots of different ways to calculate that. If you look mostly in thermo books, you'll see 2 or 3 different ways to calculate that. The way that we're going to calculate this, I believe, should look familiar because I think it's the same as what you do in your thermo book. The Smith and Van Ness thermo book uses exactly this approach. We start out by defining this as K sub A. Sometimes it's just defined as K, just capital K. I think that gets confusing because how do I tell you it's just capital K? I have to tell you like, no, I just mean just capital K, there's no subscript. Whereas here, if I give it a subscript, I can just tell you it's K sub A. So it's a little bit more specific to say K sub A. And also, as we will learn later, the A is actually a helpful subscript because it tells us what's on the other side of the product. So when we say K sub A, the A we're referring to is the activity over here. So it's useful to give it that subscript. This K sub A, if you look at Smith and Van Ness's book, which is the formulation that I use here, is split into 3 portions. There's a K0, a K1, and a K2. K0 gets us started. It gives us the K value of delta G of formation, or under like standard conditions. That's what the little circle means, which is just 298 K and 101.325 kilopascals. That's not a particularly common system for reactors. Most reactors don't run at 298 K. A lot of them run around atmospheric pressure, but not very many run at 298 K. And so K1 is an adjustment to K0 that says I usually don't operate at 298 K. I usually operate somewhere else. And then K2 is actually a further adjustment to K1 and K0 that says the enthalpy term that's inside K1 is usually not constant. If we just write K1 and ignore K2, that's the same as assuming that the enthalpy of formation or the enthalpy of reaction is constant. And that tends not to be the case. For a lot of cases, though, over the range of like 400 or 500 Kelvin, it's not a bad approximation to assume that the enthalpy of reaction is constant. And so we will often assume that it is constant. In fact, everywhere in the book, we are going to assume that it's constant. 2.23 is called the full Vant Hoff equation because it's got the K2 in it. Far, far more often, we're going to use this one, which is why it's boxed. This is what we call the shortcut Vant Hoff equation, which is K sub A without the K2, right? We just calculate K0 and we calculate K1. K0 and K1 are both defined above here. And this is what we're going to practice calculating for the rest of today. And then we may even look at tomorrow's lecture as well, calculating more KAs. we can refer to it as either Ka or KSC. It essentially means the same thing in this class because we're always going to use this shortcut version, which is K0 times K1, as pretty close to Ka in most cases. And so I'm gonna, if you have the book open, I have a little, I have my own hard copy of the book. Again, I suggest you get a hard copy of the book because it's really convenient. And I don't like looking at the computer all that much. So if you have that, leave it open because we're going to be referring to this, but I'm going to switch back over to the handwriting screen. Am I going to use Matlab in this lecture? Maybe, if we have time to it. I can demonstrate how to solve these in Matlab, but we're not doing anything here that you can't solve with a hand calculator. So I don't know if we'll have time to get to more Matlab. Maybe. Oh, I'm going to turn off that sound too. So let me switch back over to here. And I screwed this up last time. So let me double check my mapping on my Wacom tablet here. Define this real quick. There we go. Oh, I canceled it. Let's try that one more time. Click to define screen area. Here. Here. Done. And don't forget these notes that I'm writing here. Those will always get published along with the lectures. So you'll always be able to look back at these. So the equilibrium reactor, that really does not seem like it mapped correctly. Oh, it's on the whole monitor. See, there's those portions. There we go. Oh, I hit the down arrow over there. That's what happened. So the equilibrium reactor. How do we get a hard copy? It's available on the bookstore. You can order it on their website and they'll ship it to you for free. Sorry, the shipping is free. The cost of the book is $10. Generally what we're looking for, the equation that we're solving, the one that means the Gibbs energy has been minimized, is that we've got a product of all of our species. Our species are always going to be labeled A, B, C, D, E. So when you see a product term like this from A to Z, it means we're taking the product of all of the related terms of the activity raised to the stoichiometric coefficient, which is nu sub I. That is going to be equal to K sub A. And we're always going to approximate this as KSC, and KSC will be K0 times K1. And that's what we're going to focus on today, is the K0, K1 part. K0 is the exponential of minus delta G over RT. And there's a couple of subscripts on the delta G and the TR, or sorry, the T. The subscript on the T is usually an R, and that means reference temperature. So at whatever temperature the delta G up in the numerator here is reported, that's our reference temperature. It's nearly always 298. Just to remind us that those are at the same temperature, we subscript the delta G with TR. We also put a little circle on here to indicate that this is under standard conditions, which we'll get to more in a moment. The other one that we need is K1, and K1 is equal to delta H over R. So we're still going to call that T sub R. And technically it has a circle, although you'll see as we go, we tend to drop that circle, times 1 over TR minus 1 over T. I am writing that down because it's already given in the book in several different locations. And in fact, those are 224 and 225. The reason that I'm writing them down is because you should remember these equations. We're going to use these equations a lot. And so it's useful to write them down because that helps build a little bit of muscle memory for you to remember what they are. Both of the delta terms in here, we're going to see a lot of deltas in the class. All of the deltas, I think all with there's like one delta in an appendix somewhere that doesn't follow this rule. All of the deltas are defined this way. Every delta of any quantity M is defined as the sum of the stoichiometric coefficient I times the property M for whatever the I parameter happens to be. So this sum runs from A to Z, right? Whatever components we happen to have. So we would write this as something like the stoichiometric coefficient of A times whatever property of A plus the stoichiometric coefficient of B times the property of B, et cetera, all the way out to as many different components as we happen to have. When we have this particular symbol, this one, the circle that's up there, that tells us that we have a really easy way to calculate delta G, and that really easy way to calculate delta G is using the Gibbs energies of formation. And those are tabulated. That's the great thing about Gibbs energies of formation. Somebody has tabulated them for us. So anytime you want to calculate a delta G sub T sub R, it should be nu sub B times mm. No, I think oh yeah, sorry. That should be a multiplication, not a plus. Thank you. Those two are supposed to be multiplied together, not added. So if we wanted to calculate delta G sub TR with a circle on it, this would be the sum of nu sub I times delta G of formation of component I in its standard state. So that is delta G sub F comma I with a little circle on it. And that sum runs from I is equal to A, so the first species that you've got, all the way to the last species, which is Z. The nice thing about this, as I said a moment ago, these terms are tabulated. Specifically, they're tabulated in your book in the appendix. If you look in, oh, I went too far. Appendix C. So Appendix C has, or no, sorry, Appendix D. I don't even know my own book. Appendix D has lots and lots of Gibbs energies of formation for different compounds. Similarly, and so, sorry, I should say, whenever we need the Gibbs energy of formation, we just go to the table and get it. And I think that should look, again, fairly similar to the process you would have used in a reaction engineering, or yeah, you're in a reaction engineering class, a thermo class, because I think normally you'll get to similar topics. Another one that we will need, and this one we would have calculated potentially in your material and energy balances class, is the enthalpy of the reaction, which is the same sum, except now we use the enthalpies of formation instead of the Gibbs energies of formation, which again is a tabulated quantity. So both the delta G and the delta H of formation are tabulated, and those are both available in Appendix D for basically any compound that we're going to need right now. So when you're first starting off with an equilibrium reactor type problem, usually a nice thing to do, because you're probably likely to need it, is to just go through and create a little table of all of your stoichiometric coefficients for the reaction, as well as all of your Gibbs energies of formation for each component, and the enthalpies of formation for each component. Later on, we'll see that it's also useful to keep a heat capacity table too, but right now we don't need a heat capacity for anything. So let's just come up with a simple example. So this equation is used in a fuel cell. The way a fuel cell works, its overall reaction is that it combines hydrogen and oxygen into water. And I'm going to assume that this entire thing takes place in the gas phase. And so I need to balance the stoichiometry a little bit here. My oxygen gets a 1/2. There's a note about stoichiometry, which it's historically been a source of confusion in reaction engineering, because at some points the stoichiometry does matter, and at other points the stoichiometry does not matter. We are not at a point yet where stoichiometry will matter for the final answer for an equilibrium reactor. When we introduce rate laws around next Wednesday, we'll have to be a little bit more careful, because, excuse me, we'll get very different answers if we multiply this whole thing by 2 than if we were to leave it with the stoichiometry that we've got right now. At the moment, it doesn't matter. We'll calculate different intermediate values, but the equilibrium reactor will give us the same answer regardless of how we write the stoichiometries. So it can be really useful to, like I said, get a little stoichiometric table going here. So I will summarize my delta G of formation for each one and my delta H of formation for each one, along with their stoichiometric coefficients. We'll go H2, O2, and H2O. And so the stoichiometric coefficients, this kind of a table should start out looking pretty similar to the one that we would have used in material and energy balances. So we have minus stoichiometric coefficients for hydrogen and oxygen, and then we've got a +1 for water because it's one of our products. And now we have to go look up these values. I'm going to share the book screen real quick just so that you can see where to go in the book. But we actually have a nice advantage here. That's weird. Why is it doing that? Is it me or is it? It looks like it's sharing a very large chunk of my screen. Yeah, that's pretty close. If you go to the appendix in the book, shrink, and go to physical properties, you can see that the delta H's and delta G's of formations under standard conditions are just listed directly here in the table. And so you go in, find the value you want, and write it down. That's the value that you've got. The units on both the enthalpies and the Gibbs energies of formation are both kilojoule per mole. That's listed up here on the top of the table. So don't forget that, because oftentimes the units will work out a little bit strangely if you forget that those units are kilojoules per mole. If you plug them in as joules per mole, heat capacities are traditionally tabulated with units of joules per mole and joules per mole per Kelvin, whereas energies of formation are kilojoules per mole, just because they get tabulated a little bit better. So if we've got, we need to look up what it is for water. Make sure you're in table D2. So if you look up at the top of table D2, it says properties of gas phase compounds. If you're dealing with a liquid, it should be review from thermo. If you're dealing with a liquid, go get the enthalpy of formation for the liquid phase. And if we have time, we'll get to that, an example of how that would work as well. So I scroll down here to water and I see that the Gibbs energy is minus 241.8 and the enthalpy is minus 228.6. So I'm going to write those down on my notepad real quick. So Gibbs is minus 241.8 and enthalpy is minus 228.6. I routinely make mistakes there. So get into the habit of whatever. Oh, see, I just did it right there. I swapped the H and the G. I do that routinely. So let me correct that real quick. It's really easy for some of the compounds because the two numbers are so close to each other. You'd think I would have my own form for not doing that, but here we are. And minus 241.8. Yeah, I know you can't see what's in the pad. I just wanted you to see the number so you can write it down. I'm going to switch back over to the pad right now. So here's the notepad, no worries. I wrote in the values for water, for its Gibbs energy and its enthalpy of formation. Whenever you see an element in its standard state, so for example, hydrogen and oxygen here, they are typically gases at 298 and 101.325 kPa. You can kind of rest assured that both of these quantities are going to be 0, which you can look up in the book if you want. But once you see a couple of those patterns a few times, then you won't have to keep looking. So if you don't know why those are 0, don't worry about it. They are listed as 0 in the Appendix D, but the reason that they're 0 is because they're elements in their standard state. So they get 0. So if I want to then calculate my delta G and delta H, delta G sub TR. It's going to be a -1 times a 0 plus a -1/2 times another 0 plus a 1 times a -228.6, which is kind of nice, right? That's just -228.6. And don't forget the units, right? Units are kilojoules per mole. Same thing with delta H sub TR with a circle. The first two are going to be effectively 0. I'll have -1 times 0 and a -1/2 times 0. Did I mess that up again? No, I wrote it right. Yeah. -1/2 times 0 plus a 1 times a -241.8. And so our delta H is going to be equal to -241.8 kilojoules per mole. These then are the two numbers that we would put into K1 and K2. So, or sorry, K0 and K1. This is the number we put into K0. This is the number that we will put into K1. And those are the two equations that we had before. Watch the negative signs. Sooner or later, you will make an error with a negative sign because I routinely make errors with negative signs. K0 will be the exponential of minus delta G TR with a circle over R TR, which is the exponential. Here's the negative sign, right? The value of delta G TR is -228, but then we take the negative of it. So 228.6 kilojoules per mole divided by R. The T sub R that we've got here is 298.15 Kelvin. The reason that I know that it's 298.15, remember every one of those tabulated values are tabulated at 298.15 Kelvin. Usually you can just do 298. It's not going to introduce that much error if you just do 298. But 298.15 is specifically what it needs to be. Also notice the units on R. Typically when you find the units on R, they'll be listed as joules per mole per Kelvin, as opposed to kilojoules per mole per Kelvin. So usually there's a unit conversion that has to happen somewhere along the way. So here's our K1 expression. Again, I'm writing this out because it's really useful to get into the habit of writing this out because we write it so many times. We use that equation so many times that it's helpful to have it written out. And so this will look like, I'm actually going to start a new line down here. Exponential of our delta H that we just calculated, which is 241.8 divided by R. The reference temperature here is, again, 298, because that's where these are tabulated. And they're subtracted off a 1 over T, where T is whatever temperature that we want. And so this T, that's your reactor temperature. So if somebody tells you that you have an equilibrium reactor operating at 400 Kelvin, that's the T that they're talking about, right? The T that's sitting inside K1 right there, that's the reactor temperature. And so later on in the course, when we have different forms of reactors where the temperature actually varies along the length of the reactor, this T, the one that we just highlighted right there, is going to become a variable. And so we're going to have to calculate things as functions of temperature. And so with this setup, after we were to calculate those two values, we would calculate K sub A as approximately K shortcut, which is equal to K0 times K1, right? And whatever that value happens to be, will end up being our Ka value. I guess this could be a good time to switch over to Matlab if we wanted to, in order to figure out what that value is. Maybe we'll do that if we have a couple minutes here at the end, but I just wanted to go back to something I had mentioned earlier about the phase being important. And so that comment about the phase was back up here. When we wrote the original expression, I had specified a phase, right? Over here, I said, this happens to be written as though the entire reaction is operating in the gas phase. And so what's implied on each one of these, I don't think I have actually enough room right there. So this hydrogen is in the gas phase, this oxygen is in the gas phase, and this water is in the gas phase. And that's what I mean when I say this reaction takes place in the gas phase. That's not the case all the time. We will deal with a fair number of liquid phase reactions. We will deal with a fair number of gas phase reactions. And we can also have reactions where say the products are in one phase and the reactants are in another phase. And that's perfectly normal. It doesn't assume, or it doesn't require any changes to what we've got here. So for example, if we wanted this to be in the liquid phase, which is sort of the script L, do we assume ideal gases? Yeah, everything in here is ideal gas. Hooray. If we wanted to assume that this was liquid, we would have to then realize that the enthalpies and Gibbs energies of formations that we had previously tabulated were both for the gas phase. And so we have to come up with a new set if we wanted to know delta H, sorry, let's do G to try to keep these similar. We'd have to look up a Gibbs energy of formation for a liquid phase material, as well as an enthalpy of formation, too big, for that particular material, also in a liquid phase. It doesn't change anything about the calculation. The only thing that changes is which table do you go to. And so there is a table in Appendix D for gases, and that's the really extensive one. The reason it's so extensive is because people can actually just calculate these things. We don't need to measure them if they're liquid phase. And that's table T2, or sorry, D2. Let me write this. So these, if you're going in the gas phase, you'll find these in table D.2. And I will highlight that because we're going to go, a lot of your homework is going to require you to go back to table D.2 in order to find out what the enthalpies and Gibbs energies of formation are. The other ones, though, the ones in the liquid phase, and in fact, there's one other one, which is aqueous, are in table D.3. So the data that are contained in there are the same, right? It's Gibbs energies of formation, enthalpies of formation, and heat capacities. It's just if you're looking for liquids, like we're going to need here, then you're going to need them inside of the table for D3, which is for a liquid phase. And if it's for a gas, then it's table D2. And if I look up the liquid one in table D3 for water, those values, Gibbs energy of formations minus 237.1, and the enthalpy of formations minus 285.8. Those are offset by exactly the enthalpies of vaporization and entropies of vaporization. So if for some reason you need to ever calculate those, you can do it, but we don't have to need to. The other ones, though, they're almost irrelevant, right? If I'm writing this equation as gas hydrogen and gas oxygen goes to liquid water, then I would need those values, the ones that I've already got there. So if I'm solving this for all gases, then I only need the values that are in black. If I'm solving it for gas hydrogen and gas oxygen, but liquid water, then I just have to switch my water values over to the blue ones. I'm not writing any switches for the hydrogen and the oxygen here, 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 and here. I'm not writing those because I'm not going to assume that hydrogen and oxygen are in their liquid phase. It's virtually impossible to liquidize or liquefy hydrogen and oxygen, although we can. It's a cryogenic process. It's just none of the reactors we're going to deal with have cryogenics involved, so we're not worried about something like that. If we're told to use a different reference temperature, how do we get delta H and G of formation? We're not going to be switching reference temperatures around. We will have one way to adjust K given a different reference temperature and a different enthalpy of reaction, but we're never going to have to adjust delta H and delta G of formation to any other temperature. That is described in the appendix in your book. We just don't need it. We would only do that if we were doing at least in this class, what we call a Gibbs reactor, which is another type of equilibrium reactor, but we're not going to do that. We're just going to do equilibrium reactors, in which case we don't have that problem. We can always get the Gibbs energies and the enthalpies of formation at 298.15 in the phase that we want, so that we don't have to worry about subsequent adjustments. Again, all of that is, if any of that sounds different from what you would have learned in thermo, there's only two options here. A, you don't remember it correctly from thermo, or B, I'm just presenting it slightly different from thermo. It is exactly the same thing that you would have done in thermo. These enthalpies of reaction calculations are exactly what we did in material and energy balances. And so just try to modify whatever you remember from those classes to make sure it's consistent with what I've gone over here. And that'll help out. We do have a nice way to introduce a little bit of, since we've got about 8 minutes left in the class, MATLAB's vector formulations make these functions really, really easy. And so if you look in the appendix in your book, this is one of the nice things about the book is I wrote it so that it interfaces nicely with MATLAB, because these kind of calculations for delta H's, they get really tedious if you do them by hand. If you were to take this class by hand, you can guarantee on the exam, or sorry, if you were to take this class in person, because we don't have a pandemic, I guarantee you on the exam, I would ask you to calculate one of these by hand. But at the same time, I would only ask you to do it like once. Every other time I would just give you the value, because it just gets tedious to calculate these things over and over. And one of the things that we try to teach you in this degree program is certainly figure out how to do it by hand, because you need to know how to do it by hand in some cases. But for these tedious ones, we also want to show you what's the way that we would routinely calculate something like this. If we are using MATLAB, then the routine way that we would calculate this is given in the appendix. And here again, my screen is a little bit big. Give me a check mark in the participants window if what you're seeing is just the book, but give me an X if you're seeing like a big chunk of black space to the left of the book. Because what I'm seeing on my side suggests that there would be a big chunk of black space on the left side of the book. That big chunk of black is there? Okay. Let me move it over here. How about that? That should be better. There we go. That is so cool. I can watch all the red X's shift over to the green checks. That's so cool. Again, the things that are enjoyable as a teacher. So if you check the appendix, this vector formulations in your book, we can practice a little bit of this right now. The vector formulations for delta calculations and for sums in particular are given right here. So these come up so often that it's really useful to be able to type them into MATLAB and not worry about getting the sums right and wrong. Like you just saw me get that wrong a moment ago when I wrote it, right? I had a little plus sign where I wasn't supposed to have one. If you get into the habit of using the vectorized notation inside MATLAB, you can actually write code that reads very, very similar to the way that the equation is written. And that sort of sum of a product comes up a lot. And so I've given you a couple of examples here of ways that you can calculate those sums. So in the last like 4 or 5 minutes that we have that, the reason your screen is doing that is because you're looking onto Adobe Reader, but the add text comment is dragged to this. Oh, is that what it is? Yes. Thank you, John. Now I know what it is. Perfect. Thanks, John. So let's take a quick look at how we can use something like this to calculate those enthalpies of formation, or sorry, enthalpies of reaction, Gibbs energies of reaction, using MATLAB much more quickly than we would otherwise need to do. So I'm going to switch back over to MATLAB here really quick. Give myself a quick script here. And so the general syntax looks like create a vector of each of the components that correspond to a species, right? So our vectors will generally go in the form of H2, O2, and H2O, right? Every element of our vector will be organized in exactly this way. And that's organization you have to do. MATLAB cannot do that organization for you. You have to keep track of that organization. So for example, my delta H of formation of each component is going to be in the order of enthalpy of formation for hydrogen, enthalpy of formation of oxygen, and enthalpy of formation for water. And we're going to say all gas phase. So my enthalpy here was 0, my enthalpy for oxygen was 0, and my enthalpy of formation for water in the gas phase was minus 241.8, and that's kilojoules per mole. Similarly, my Gibbs energy of formation is 0, 0, and minus 228.6, also kilojoules per mole. And I have a stoichiometric a vector of stoichiometric coefficients, which is -1, -1/2, and +1, right? And again, that's H2, O2, and H2O. Are commas necessary when creating vectors? No. You can use spaces or semicolons for this. The shape of the vector doesn't matter for what we're doing. Eventually, it will matter, and I will point out when it matters. Right, and so our enthalpy of reaction, dH, if I say it in words, right, if you look back over at the equations in chapter 2, the way that you would say that in words is that the enthalpy of reaction is equal to the sum of the products of nu sub I times enthalpy of formation for each species I. The nice thing about this is I can write a function or an expression in Matlab that reads almost exactly like that, right? I can use the function sum, and I can say, what do I want to sum up? I want to sum nu times DHF, right? And that'll give me a unit of kilojoules per mole. That's really advantageous because I can now read the book or read my notes or read the problem statement and say, okay, I got to calculate the sum of nu times DHF for every component. And then when I code it, it looks like the sum of nu times DHF for every component. And so that's a great way to eliminate errors, right? It's one less algebraic step that you have to take when you're calculating something. And so it limits the number of times that you can create an error. Not that it's impossible, you're still going to catch me creating errors, but now we have our DH and our DG, and they both look very similar. It's very easy for me to tell if I've made a mistake in one and not a mistake in the other because they all look very, very similar at this point. I'm going to do the remaining two steps since we have about 2 minutes left of calculating the Ks, since we need the Ks. If we need K0, that's equal to the exponential of minus dg divided by r times tr. And if we need K1, exponential of dH divided by r times a quantity 1 divided by tr minus 1 divided by t. So a couple of things to note right here. One, Matlab is not useless when it comes to its error messages. Its error messages are actually somewhat helpful. So I've left a couple of errors in this code so that when I run it, we can try to use the debugging tools. Oops, don't save that. If we submit Matlab code, do we have to provide units as comments? No, but I really strongly suggest that you get into the habit of doing that, precisely because there's an error in my code right now that is a unit error problem. But you don't have to do that. Do you have to input the table manually? You can copy paste. That's okay, as long as you get it to copy paste in the right form. I usually enter them manually because most of the problems that we have aren't more than about 5 or 6 components. If I run this script, I get an error. This is actually a really nice way to set up your scripts. I've done what I think I need to do. Right, I think I've got the questions or the values calculated correctly, but I run the script and I get an error. It says an unrecognized function or variable r. Not a problem. All that's telling me is I have forgotten to define r. So right up above here, I say r is 8.314, and I note that it's joules per mole per Kelvin. And I say, okay, I think I've solved it again. Let's try and run that script. Clear this and run it again. I get another error, right? It says, oh, you forgot to define T sub r. That's actually a really convenient way to set up a lot of problems, is you just define everything that you think you need and then just see what happens when you run it and you look for these unrecognized functions or variables. And it's just MATLAB's way of telling you, hey, you forgot something. So remember, TR is always 298.15 in Kelvin. I can tell just from looking at line 14 that I need a T as well. So maybe we want to calculate this at 400 Kelvin. And that, right, to me looks like we've calculated everything. Let's see if we've got it. Okay, I ran that script. It didn't have an error. Presumably that would be all I need to do. Matlab can't catch the error that's in here. The error that's in here right now is that R has units of joules per mole and my DHs have units of kilojoules per mole. Matlab will never ever catch that error for you. It'll just calculate a new value of K0 and K1. And so I need to take both of these and divide by 1,000. Right, that's not an error that Matlab would ever catch for me. And so that's why I always recommend that you put the units on here so that when you do a unit conversion like that, I now know that these are in units of joules per mole and not kilojoules per mole. And now the values of K0 and K1 would be correct. And if I calculate, or if I ask for K0 times K1, I just get about 1, but I think that's because I forgot to run it. No, it's about 1, evidently, under those conditions. And so it's a very convenient way to set up your scripts so that the things that you're calculating look as close as possible to the actual things that are written inside the textbook. And so this goes up to about problem 1.4. It's just practicing these types of calculations. So we're actually at a good stopping point. It's 3:52. We're going to have another lecture on Friday. I'll still be here on Friday, but remember our Friday lectures are all going to be handled by John. John's sort of our super TA. He's helping me co-teach this particular course. So I will hang out and answer questions for a little bit, but I am not going to present any new material because we're right up there at the end of class. So feel free to take off. But if you have any questions, let me know. I will hang out and answer them. Oh, did I convert units wrong? Kilojoule. Oh, yeah, you're right. Is it 1 kilo? Yeah. Maybe that'll fix my. Yeah, that looks better. The KSC was supposed to be like enormously in the favor of hydrogen and oxygen. No assigned office hours unless asked for. Is that correct? Yes and no. So the way that office hours are going to work, because I'm trying to cut down on the amount of email, is probably later today or tomorrow. I'm going to send out a link and I'm going to add a posting to Canvas, or I'm going to send an email describing this. I'm going to put something on Canvas where you can go into my Google Calendar, and I'm going to have different slots in there, and you can just pick a slot and I will be here. I will send you a Zoom meeting at the time that you want. So it won't be fixed. You'll just be able to pick whatever time happens to be convenient for you at that week or that day or something like that. So yeah, they won't be fixed in the sense that I'm not just going to sit somewhere for an hour, but the time slots will be fixed and you'll just be able to sign up for a time slot. It's awkward to sit here in silence, so I'm just going to turn that music on again, but I'm just going to sit here for a couple of seconds. Let me know if when I start talking that the music is drowning out my voice and I can adjust the relative volumes on them. Song name that I used right before lecture yesterday, I don't know. It's one of the ones by Kevin MacLeod. I just don't I don't remember which one it was, but if you Google Kevin MacLeod, if you scroll up a little bit in text, I posted his name and you should be able to find it. I don't remember. How much does a pen plotter cost? I'll unfortunately a fair amount right now. If you want the version that I was using on the website, I think it was like $4.99, something like that. But I liked that one because it was already interfaced with Python, so I didn't have to build my own interface. Yeah, I know, it's really expensive. If you go to like a surplus store somewhere for an office, if it's an old office for an architect, they used to use them for architectural drawings, and so you might be able to get one cheaper. Or if you look on like eBay or something like that, you might get an older one. But again, then you kind of have to build your own interface. You're welcome. There's only 9 of us here, so I'm going to switch chat back over to public. Hopefully the pen plotter will be on my office door this summer. If the campus is open and I'm allowed to go back there and work on it. I got it so that people can use it on my door. It'll be sort of like bolted up onto the door and it'll do stuff. John, did you label yourself as Super TA or did I do that? I can't remember it. I don't have a problem with that. I think it's great. Okay, yeah, that's fine. What am I using the pen plotter for? Yeah, the idea will be it'll be mounted to my door, and if you want to leave like an away message or you just want to have it like draw you something, you'll be able to type a few commands into a keyboard and it'll actually trace out whatever you ask it to do. Which is, it's close to ready to go. It takes like probably 2 more days solid coding plus a couple of days to mount it. But I can't obviously do that because campus is closed. All right, it's about 4 o'clock, so I'll wait around about another minute in case anybody's got another question, but otherwise I'll wrap it up in about a minute. Okie dokie, that's about it. Thanks everybody for hanging out with me for a little while. I will, actually, John, I will see you on Friday, because you'll be up on Friday. Let's go ahead and stop that recording. See y'all in the next class.